Welcome to section 7.3 part 1, an introduction to the polar coordinate system. Polar coordinates are another way to describe where a point is in the plane. So typically we have a point x comma y, and in polar coordinates we're going to describe the placement of that point in terms of r and theta. R is the directed distance from the origin to the point P. And by directed, I mean r can be positive or negative, and we'll talk about what r negative means in a minute. Theta is the directed angle from the polar axis, which is the positive x-axis, to the line OP. So theta equal positive is counterclockwise, theta equals negative is clockwise. So let's take a look at some examples here. We're going to plot these points on polar graphing paper. Now, polar graphing paper you can make yourself. Each ring is how far you are from the origin. So this first ring is the set of all points r equal 1. The distance of every point on this circle is 1 unit from the origin. The second circle out would be r equal 2, so on and so forth. And these angles are our common unit circle angles. So this is pi over 6, pi over 4, pi over 3, ... So when I'm plotting a polar point, I go to the angle first. So I go to the angle pi over 3, that's right here, and then I look at r. If r is positive, I'm going to go 2 units out into the quadrant that pi over 3 is in. So let me erase this stuff. 1, 2 units out, there's point A. All right, let's do 3 negative pi over 6. So I go to the angle negative pi over 6, that's right here, and I go 3 units out. 1, 2, 3, and this is B. All right, now here we've got negative r. Again, go to the angle first. Go to 5 pi over 6, that's here. And then instead of going 3 units out, you're going to go 3 units in the opposite direction because r is negative. So I'm going to go 1, 2, 3. So B shares a terminal side with C. B and C lie, well, they're the same point in the plane. So that's what r negative does. Go in the opposite direction from the quadrant that your angle is in. Let's do another one with r negative. I go to the angle pi over 2, which is up here, positive y-axis, and I go 2 units in the opposite direction. 1, 2. So this would be point D, all right? E tells you what to do when r is 0. When r is 0, you're going to go 0 units out from the origin, so the angle pi is irrelevant. If you're 0 units out, you're at the origin. So it doesn't matter that that was pi over 2. It could have been pi over 7. We would still be here at the origin. Okay, but what about if theta is 0? So F has r equal 2 and theta equals 0. The angle 0 is positive x-axis. This is theta equals 0. So I'm somewhere on that line, and here I go 2 units out. 1, 2. So this is F. All right, 2 more. Go to the angle 2 pi over 3, that's right here, and go 2 units out. 1, 2. So this is G. And finally, for H, I'm going to go to the angle pi, which is the negative x-axis, and I'm going to go 3 units in the opposite direction. 1, 2, 3. So this is H. All right, now let's sketch some regions in polar coordinates. Let's do the middle picture first. So r is being restricted between 1 and 2. R equal 1 is a circle of radius 1. R equal 2 is a circle of radius 2. So I'm somewhere between those 2 rings. So if there were no restrictions on theta, I would fill in that whole donut. But now I go over here and I look at theta. Theta is restricted to be between 0 and pi. So theta equals 0 is here. Theta equal pi is the negative x-axis. So I'm anywhere on the top half of that donut. All right, now let's go over here to r less than 1. Again, r equal 1 is a circle of radius 1. So if I want r less than 1, first of all, I'm going to dot in this circle to indicate these points are not in my region. And then r less than 1 is going to be any point inside of that circle. No restrictions on theta. And over here is another extreme. Here there are no restrictions on r. So if we just look at theta between 0 and pi over 4, theta equals 0 is the positive x-axis. This is theta equal pi over 4. And so I would sketch all of these points are going out to infinity. And you might just quit right there. And if you did, you would be half right. That's only half of the story. Remember, r can be negative. So if r is negative, that's going to push us over here. And so we're also going to pick up all of those points. So this is r positive and this is r negative. Okay, coordinate conversion. There's 4 equations and they come in sets: polar to rectangular, rectangular to polar. The way I remember them is just with a triangle. For example, this first equation, x equal r cosine theta, if you look at this triangle, you can say cosine theta is adjacent x over hypotenuse r, and then solve it for x, and you get the first equation, x is r cos theta. Similarly, you can get y equals r sine theta. This equation, r squared is x squared plus y squared, is just the Pythagorean theorem. And then tangent theta is y over x. That's going to give you theta. And if we restrict theta to be an angle between 0 and pi over 2, that will give you 2 values of theta. So typically when you go from rectangular to polar, you're going to pick up 2 values of r, 2 values of theta, and then you'll need to put your choices together correctly. And I'll show you how to do that. So let's do the easy direction first. Go from polar to rectangular. Here, there are no choices to make. You just use the formulas x is r cos theta, y is r sine theta. And so cosine of pi is -1, so this is -2, and this is 0. And so x comma y is -2, 0. Now, we didn't need equations for that. We could have just gone straight to this point. This says go to the angle pi, which is over here, and go 2 units out, 1, 2. And so there I am at xy equal -2, 0. So some of these you just don't need equations for, you can just graph. Okay, next one. X is, again, r cos theta. Cosine of pi over 6 is √3 over 2. So this is √3 times √3 over 2, which is 3/2. And sine of pi over 6 is 1/2, so this is √3 over 2. So our xy is 3/2, comma, √3 over 2. Okay, now let's go in the other direction. Find 2 sets of polar, both with theta going between 0 and 2 pi. So the way I do these, I like to find r first. R squared is x squared plus y squared. In this case, x squared is 1. And y squared is also 1 because we have -1 squared. So r squared is 2. So that gives me r is plus or minus √2, 2 values of r. Tangent theta is y over x, which is -1 over 1, which is -1. So that tells me that theta is 3 pi over 4 or 7 pi over 4. Okay, tangent is the slope of the terminal side. So if tangent theta is -1, I'm up here or I'm down there. Okay, now I need to put my r's together with my thetas correctly. So here's the part where you want to plot the actual point you're given. My point, x equal 1, y equals -1, is in quadrant 4. So I'm not up here, I'm down here. I'm in quadrant 4. So if I choose the positive value of r, √2, I want the angle also in quadrant 4. I want 7 pi over 4. If I choose -r, I don't want it to be in this quadrant. I want to be up here in quadrant 2 so that when I use the negative value of r, it will bounce me back into quadrant 4. So I want to use 3 pi over 4. So those are the 2 choices that are going to work. Okay, what are the other 2 choices that wouldn't work? Well, I could have chosen -√2 and 3 pi over 4, sorry, that's one of the ones that does work, 7 pi over 4, or I could have chosen √2 and 3 pi over 4. Now what's wrong with this guy? negative root 2, 7 pi over 4, if I go to the angle 7 pi over 4, I'm in quadrant 4, negative root 2 is going to push me back up into quadrant 2. This is in the wrong quadrant. My point is in quadrant 4. Likewise, this point here is in quadrant 2, not in quadrant 4. So some students write down all 4 choices and scratch out the ones that don't work. I typically go straight for the 2 ones that will work. Okay, let's do another one. R squared is x squared plus y squared, which in this case is 0 squared plus 2 squared, which is 4. So r is plus or minus 2. Tangent theta is y over x. 2 over 0 is undefined. So I know theta is pi over 2 or 3 pi over 2. Those are the 2 angles between 0 and 2 pi where tangent is undefined. Now, to figure out how to pair these r's with these thetas, I plot my point. That's x is 0, y is 2, so I'm up here on the positive y-axis. So if I choose the positive r, which is 2, I want to choose the angle that's giving me the positive y-axis. That's pi over 2. And if I choose negative r, I want to choose 3 pi over 2. Those are my choices. All right, one more. I've started us out. Again, r squared is x squared plus y squared. So that gives me, for this problem, r is plus or minus 2. Tangent theta is negative 1 over root 3. So let's see. Negative 1 over 3, that's a negative slope, and it's gradual. Tangent theta is the slope of the terminal side. So that's giving me 5 pi over 6, or 11 pi over 6. Now, where does this point lie? Well, x is negative and y is positive. So I'm in quadrant 2. So if I pick the positive value of r, which is positive 2, I want the angle, that's 11 pi over 6, sorry about that. I want the angle that's in quadrant 2. I want 5 pi over 6. And if I take negative 2, I want the angle that's in quadrant 4, which is 11 pi over 6. So there you go. Okay, equation conversion. Again, there's an easy direction and a direction that requires a little bit more thought. We'll do the easy direction first. If you're going from rectangular to polar, everywhere you see an x, you put in r cos theta. Everywhere you see a y, you put in r sine theta. So for y, I put in r sine theta. And for x, I put r cos theta. So I'll get r squared cosine squared theta. Now I want to solve for r, and I'm going to do something that you won't normally see me do, which is divide both sides by a variable. I'm going to divide both sides by r. This gives me sine theta is r cosine squared theta. And the reason I feel safe doing that is r equals 0 is the origin. When you divide by r, you seldom lose the origin. There's so many other ways to get it that you're seldom going to lose that as a solution. So I've got that written here, but you should feel comfortable dividing both sides by r if you have to in a polar equation. So finally, let's solve for r. R is sine theta over cosine squared theta. And you could leave it like that, or you could write that as tangent times secant, either or. All right, y equals 2. R sine theta equals 2. Solve for r. R is 2 over sine theta, which is cosecant theta. So that's interesting. We're seeing that a horizontal line is given by r equals 2 cosecant theta. And in fact, all horizontal lines are going to be given by r equals 2, not 2, but some number times cosecant theta. And vertical lines are going to be r equals some number times secant theta. So for example, x equal 1. If we want to convert that to polar, that's r cos theta is 1. So r is secant theta. All right, now let's go in the other direction. R equals 2. I don't need any equations for that. I know that's a circle of radius 2 centered at the origin. So that's x squared plus y squared equals 4. But suppose I didn't know that. Like, how would I just get that if I didn't know that? Well, over here I've got a list of desirable quantities that you want if you're going from polar to rectangular. Everywhere you see an r squared, you could replace it with an x squared plus y squared. If you see an r cos theta, you can replace it with x so on and so forth. You can read. And so what could I do here to get an r squared? I could square both sides. R squared is 4. Now replace the r squared with x squared plus y squared, and you've got the equation I had before. All right, next one, r equals secant theta. Well, secant theta is 1 over cosine theta. I like r cosine thetas because I can change those over to x's. So I'll multiply both sides by cos theta. R cos theta is x, so I get x equal 1, which we saw up above. I did that problem before. All right, now the fun problem. This is the type of problem you're going to have to do in math, in Calc 3, because we'll be doing double integrals over regions in the plane, and you'll have to set up the limits of your double integral, and they will involve describing a region like this with polar inequalities. And so here's how I start. First, I do the limits on r. So you take some rays, starting at the origin and emanating out. The value of r, where those rays hit the region, is where r starts. In this case, we're in the region right from the get-go. So r is starting at 0. R is leaving on this line. R is leaving on that line. The rays leave when r hits that line. So that's the line x equal 1 over root 2. But we have to convert that to polar. So that's r cos theta is 1 over root 2. So r equals 1 over root 2 secant theta. That's the upper limit on r. 1 over root 2 secant theta. All right, and now for theta, I want to ask, for what values of theta do I have these rays going through the region? Well, my rays start here at the positive x-axis, which is theta equals 0. So the lower limit on theta is 0. Upper limit on theta is the value of theta that corresponds to this line here. And I can just see that. A lot of these you don't need any equations. This is x equal to y on this line. 1 over root 2, 1 over root 2 is on the line. Y equals x, so that must be the angle pi over 4. All right? And so those are the inequalities that describe the region. If you couldn't, let's say you couldn't see the angle right off, let's say it wasn't something as easy as pi over 4, you could always use tangent theta is y over x. In this case, that would give me tangent theta is 1. And then I'd know, oh, I'm looking for the angle in quadrant 1 whose tangent is 1, and I would come up again with pi over 4. Okay, and that's the end of this section.